made up of hundreds of protons and neutrons that are made up of 3 quarks. This is what we're going to talk about. And as you see, so if this is the mass, you have different ways of producing the particle, cross-section versus its mass. So in our case, it's W and Higgs together, which is this mechanism, but you could have this one or this one. And then you have different ways that it can decay. So for low mass, the probability of decay is mostly to this bottom-anti-bottom pair, which is our case. So this is what I'm particularly studying. But then at high mass, you can search over here. So this is harder to search. This is easier to search. And as you see, for the first time in 8 years, the Tevatron experiment, so our experiment and its friendly experiment D0, have put together 1,000 scientists, roughly 200 of them searching directly for the Higgs boson. So I am just one of them. And then, for the first time since 2001, so I told you this region was excluded, this region was excluded, but now for the first time the territory of Higgs boson excluded even more. So if you believe a 5% chance of being wrong, we excluded this region from 160 to 170, which corresponds to these 4 atoms over here being excluded, the mass corresponding to those atoms. And if you believe 10% chance, this area is even larger. So as we gather more data, we will exclude more of this region until we will finally discover the Higgs boson. So either we see it is or we see it doesn't exist. So bear in mind that the competition, friendly competition for the Tevatron accelerator is the Large Hadron Collider Accelerator in Switzerland, an international collaboration that starts this year, and they will be they will be definitely in a few years discovering the Higgs boson or proving it is not there. So where do we all start with? If particles didn't have mass, they would be going around the universe at the speed of light, so they couldn't stay together to form those protons and neutrons that form us. So nuclei don't exist, atoms don't exist, molecules don't exist, cells don't exist, we don't exist. So searching for the origin of mass is one of the fundamental questions we have to understand about the universe in order to understand how it came about. So we made the first breakthrough in 8 years to exclude some of its territory, and as we collect more data, in 1 year we will have excluded more, and then the LHC will come and exclude everything and prove if the Higgs boson does exist or doesn't exist. So yeah, that was all. Thank you very much.
Wow, sounds deep. Anyway, any questions from the audience? Yeah, go ahead.
Okay. When you can you go back to your slide where you have this picture of tracking the particles before? Oh, okay. So, yeah. I mean, you have these protons and antiprotons collide. They something else happens. You have your detectors that you measure. So somehow I'm not able to connect this plot that you showed with that.
Okay.
How the particle moves in the detector.
Yes. A very good question. So this is not the geometrical description. This is just a schema where time flows from left to right.
Yeah.
So this means this happens first. 2 particles collide, and then a new particle is produced that travels for some time. This is why I call it virtual. And then it decays to 2 other particles, and they decay to other particles. And it is these particles here that we see in the detector.
Okay.
So it is these particles here that form those particles that we see here. So the electron would look this way, the muon would look this way. The quarks from the two BB bar that you're seeing there makes jets like that. So showers of particles, and the neutrinos are not seen in the detector. So they are seen as missing energy, as if energy were not conserved, but it is, only that the neutrinos are not detected, and they carry away energy and momentum. So you see them as an imbalance in energy. So from final state particles like that, so those 2 jets, an electron or a muon, and those missing energy, you infer the initial particles, which would be, so from those that you measure in the detector, you reconstruct through algorithm and analysis, and you reconstruct this event. And see how often do you see a Higgs boson produced together with a W boson. And you distinguish it from other particles that through their decay produce the same particles like these ones.
Okay, so my next question would be then, I mean, the other particles other than Higgs bosons, I don't know, but I'm sure there are algorithms or whatever to detect that if they are present and what are those particles.
Yes, we have to distinguish things on the background,
But then since Higgs boson, you don't know if it exists or not, how do you come up with an analysis saying that it exists or not? I mean, when you trace these back, to other particles. Those particles are identified and you know about it. Now Higgs boson, they are not identified, but then how do you come up?
Okay,
how do you find something that you don't know if it exists or not?
Yes, I understand. I understand very much. We don't know if it exists experimentally. However, there is a theory, that predicts what the Higgs boson should look like. So
Okay.
and what its possible mass should be. So basically, you have to put back together the two jets, the two quarks, and see what is their mass. And then you should expect to see the probability that it is produced. You should expect a bump where it is there. But this bump is so small, it's like looking for a needle in a billions of high-stats. It's very, very small. This is why you have to do complex analysis statistics to distinguish between signal and background. But imagine that the theory predicts a certain probability, right? And then if you predict a number of events, let's say 100, and then with the Higgs boson is 0.1, let's say, but this is exaggerated to be even smaller. Then if you see 100.1 plus or minus 0.001, so with very good precision, you could say, yes, we have the Higgs boson. It's all a matter of seeing more events than your background prediction, and then being sure your uncertainty is so small to prove that whatever is else is something else than the background, and if it has the probability, properties of the Higgs boson, then it is a Higgs boson. Yes. It's only signal and background you have to compare. Yes.
Can we take second question from Wilson?
Yes.
So what happens if the Higgs boson doesn't exist?
Yes, very good question. What happens if the Higgs boson doesn't exist? So not that we haven't discovered it yet, but we have discovered it doesn't exist. So then something very interesting happens. Some people say it's good, some people say it's bad. So it means that all our standard theory that explains all those three forces, that explains everything we know so far, and has been proven for every experiment in the last 30 years would fall. So then it would mean that the theorists would have to go back to their papers or their computations, calculators, and then come up with a new theory. And who knows, maybe this new theory would solve all the other inconsistencies that the standard model still has. But for 45 years, this is a 45-year-old theory, people have not come up with something new. So it's hardly imaginable that in a matter of a few years they will come with something totally new that they haven't done in 45 years. But if Higgs boson doesn't exist, then a very interesting moment comes in science, which could be equivalent with the equivalent of 100 years ago when the radiation of atoms was not explained, and Planck come with something totally new that nobody thought about and revolutionized the way we think of the universe. Maybe there will be something similar in this case if the Higgs boson does not exist. On the other hand, if it does not exist, it would be harder to apply for funding for the next accelerator, which is supposed to be the International Linear Collider, because they would say you haven't seen here anything. Why would you believe the next accelerator, more energetic and more expensive, would finally see something? So,
yeah, go back to the paper and pencil and write down your equation, figure out a new theory before we give you more money. Yes, right. Okay, so
thank you very much.
So this concludes the first presentation. Thank you.